Chapter 4, Motion in a Plane. Topic: Introduction, Scalars and Vectors, Multiplication of Vectors by Real Number, Addition and Subtraction of Vectors, Graphical Method, Resolution of Vectors, Vectors Addition, Analytical Method, Motion in a Plane, Motion in a Plane with constant acceleration, Relative Velocity in a two dimension, projectile motion, यूनिफॉर्म सर्कुलर मोशन, समरीज एंड पॉइंट टू पॉन्डर। उसके बाद एक्सरसाइज है, एडिशनल एक्सरसाइज है, ठीक है। इंट्रोडक्शन। In the last chapter, we developed the concept of the position, displacement, velocity, and acceleration that are needed to describe the motion of an object along a straight line. We found that the directional aspect of these quantities can be taken care of by positive and negative sign, as in one dimension only two direction are possible, but in order to describe motion of an object in two dimensions, a plane or three dimension space, we need to use vector to describe the above mentioned physical quantities. Therefore, it is first necessary to learn the language of vectors. What is a vector? How to add, subtract, and multiply vectors? What is the result of multiplying a vector by a real number? We shall learn this we shall learn this to enable us to use vectors for defining velocity and acceleration in a plane. We then discuss motion of an object in a plane. As a simple case of motion in a plane, we shall discuss motion with the constant acceleration and treated in detail the projectile motion. Circular motion is a familiar class of motion that has a special significance in daily life situations. We shall discuss uniform circular motion in some detail. The equations developed in this chapter for motion in a plane can be easily extended to the case of three dimensions. Scalars and vectors. In physics, we can classify quantities as scalar or vectors. Basically, the difference is that a direction is associated with a vector, but not with a scalar. A scalar quantity is a quantity with the magnitude only. It is specified completely by a single number along with the proper unit. Example, the distance between 2 point mass of an object, the temperature of a body, and the time at which a certain event happened. The rule for combining scalars are the rule of ordinary algebra. Scalar can be added, subtracted, multiplied, and divided. Just as the ordinary number, for example, if the length and breadth of a rectangle are 1.0 meter and 0.5 meter respectively, then its perimeter is the sum of the length of the four side. 1.0 meter plus 0.5 meter plus 1.05 1.0 meter plus 0.5 meter is equal to 3.0 meter. The length of each side is a scalar, and the perimeter is also a scalar. Take another example. The maximum and minimum temperature on a particular day are 35.6 degrees Celsius and 24.2 degrees Celsius respectively. Then the difference between the two temperatures is 11.4 degrees Celsius. Similarly, if a uniform solid cube of aluminum of side 10 centimeter has a mass of 2.7 kg, then its volume is 10 minus 3 10 minus 3 meter cube a scalar, and its density is 2.7 into 10 the power 3 kg, 3 kg meter minus q a scalar, and its density is 2.7 into 10 the power 3 kg meter minus meter cube a scalar. A vector quantity is a quantity that has both a magnitude and a directions, and obey the triangle law of additions or equality, the um, para, parallelograms law of addition. So a vector is specified by giving its magnitude by a number and its directions. Some physical quantity that are represented by vector are displacement, velocity, acceleration, and force. To represent a vector, we used a boldface type in this book. Thus, a velocity vector can be represented by a symbol V, small v. Sign bold face is difficult to produce when written by hand. A vector is often represented by an arrow placed over a letter, says vector v. Thus, both v and the vector v represented the vector velocity vector. The magnitude of a vector is often called its absolute value, indicated by bold v equal to v. Thus, a vector is represented by bold face. Example by a p q r x y, and respective magnitude denoted by light phase a p q r x y. Position and displacement of vectors. To describe the position of an object moving in a plane, we need to choose a convenient point, says O as origin. Let P and P arc be the position of the object at time small t and t arc respectively. Figure 4.1a. We join O and P by a straight line. Then OP is the position vector of the object at time small t, and arrow is marked at the head of this line. It is represented by a symbol small r. OP is equal to small r, and the point P arc is represented by another position vector OP denoted by small arc small r arc. The length of the vector r represent the magnitude of the vector, and its direction is the direction in which P lies, as seen from O. If the object moves from P to P arc, the vector P arc with the tail at P and tip at P arc is called the displacement vector, corresponding to the motion from point P at time t to point P arc at time small t arc. Position and displacement vector. Position A. Positions and displacement vector B. Displacement vector PQ and different course of motion. PQ and different course of motion. Displacement vector. It is important to note that displacement vector is a straight line joining the initial and final position and does not depend on the actual path undertaken by the object between two positions. For example, in figure 4.1, be given the initial and the final position as P and Q. The displacement vector is the same PQ for different path of journey. Same P A B C Q P D Q and P B E F Q. Therefore, the magnitude of displacement either less or equal to the path length of an object between 2 points. This fact was emphasized, emphasized in the previous chapter also. We'll discuss motion along a straight line. Equality of vectors. Two vectors A and B are said to be equal if and only if they have the same magnitude and same direction. Figure 4.2a show two equal vector A and B can easily check their equality. Shift B parallel to itself until its tail Q coincides with the of a example Q coincide with O, then since their tip S and P also coincide, the two vectors are said to be equal. In general, equality is indicated indicated as A is equal to B. Note that in figure 4.2 B vector A arc and B arc have the same magnitude. They are not equal because they have a different direction. Even if we shift B arc parallel to itself so that its tail Q arc coincided with the tail O arc of A arc. The tip S arc and B arc does not coincide with the tip P arc of A arc. Additions and subtraction of scalar make sense only for quantities with the same unit. However, you can multiply and divided scalar of different unit. In our study, vector do not have fixed location, so displacement a vector parallel to itself leaves the vector unchanged. Such a vector are called the free vector. However, in sample physical equations, location or line application of a vector is important. Such a vector are called localized vector. Two equal vector A and B. Two vector A arc and B arc are unequal, so they are of the same length. Multiplication of vectors by real number. Multiplying a vector A with a positive number lambda gives a vector whose magnitude is changed by the factor lambda, but the direction is the same as that of A. Del A is equal to lambda A. Lambda A is equal to lambda A if lambda is less than 0, greater than 0. For example, if A is multiplied by 2, the resultant vector to A is the same direction as A and has a magnitude twist of A as shown in figure 4.3. Multiplying a vector A by a negative number minus lambda gives another vector whose direction is opposite to the direction of A and whose magnitude is lambda time A. Multiplying A gives a vector A by negative number, say minus 1 and minus 1.5, we give a vector as shown in figure 4.3b. A vector A and the resultant vector after multiplying A by a positive number 2. B. Vector A and resultant vector after multiplying it by a negative number minus 1 and minus 1.5. The factor lambda by which a vector is multiplied could be a scalar having its own physical dimensions. Then the dimensions of lambda a is the product of the dimensions of lambda and a. For example, if we multiplying a constant velocity vector by duration of time, we get displacement vector addition and subtraction of vectors and graphical method. A mentioned in section 4.2, vectors by definition obey the triangle law or equality. The parallelogram law of addition. We shall now describe this law of addition using the graphical method. Let us consider two vectors A and B mm, that lies in a plane as shown in figure 4.4a. The length of the line segments representing these vectors and proportional to the magnitude of vectors. To find the sum a plus b, we place vector b so that its tail is at the head of vector a as in figure 4.4b. Then we join the tail of A to the head of B. This line OQ represents a vector R that is the sum of the vectors A and B. Since in this procedure of vector additions, vectors vectors arranged head to tail. This graphical method is called the head to tail method. The two vectors and their resultant from three sides of a triangle. So this method is known as a triangle method of vector addition. If we find the resultant of b plus a as in figure 4.4c, the same vector r is obtained. Thus vector additions is commutative. A plus b is equal to ab. The addition of vector also obey the associative laws as illustrated in figure 4.4. The result of adding vectors a and b first and then adding vector c is the same as the result of adding b and c first and then adding vector a plus b plus c is equal to ab plus b plus c. What is the result of adding two equal and opposite vector? Consider two vectors a and minus a show in figure 4.3. Their sum is a plus a minus a Since the magnitude of two vectors are the same but the direction are opposite, the resultant vector has zero magnitude and is represented by zero called a null vector or a zero vector. A minus a is equal to zero, zero is equal to zero. Since the magnitude of null vector is zero, its direction cannot be specified. The null vector also results when multiplying a vector a by the number zero. The main properties of zero are a plus zero is equal to a, lambda zero is equal to zero, zero a is equal to zero. Vector A and B vector A and B added graphically. Vector B and A added geographically, illustrating the associative law of vector addition. Two vectors A and B, minus A minus B is also so. Um, B subtracting vector B form vector A. The result is R2 for comparative addition of vector A and B. R is also shown. What is the physical meaning of a zero vector? Consider the position and displacement vectors in a plane as so in figure 4.1. Now suppose that an object which is at p at time t moves to p arc and then come back to p, then what is its displacement? Since the initial and the final position coincide, the displacement is a null vector. Subtraction of vectors can be defined in terms of a division of vectors. We divide the difference of two vectors A and B as sum of two vectors A and B, A and minus B. A minus B is equal to A plus minus B in bracket. It is so in figure 4.5. The vector minus b is added to vector a to get r2 is equal to a minus b. The vector r1 is equal to a plus b is also so in the same figure. For comparison, we can also used for parallelogram method to find the sum of two vectors. Suppose we have two vectors a and b. To add these vectors, we bring their tails to a common origin as shown in figure 4.6. Then we draw a line from the head of a parallel to B and another line from the head of B parallel to complete a parallelogram OQSP. Now we joined the point of the interaction of these two lines to the origin of the resultant vector R is directed from the common origin along the original OS of the parallelogram. 4.6 in figure 4.6 see in the triangle law is used to obtain the resultant of A and B, and we see that the two methods yield the same result. Thus, the two methods are equivalent. Two vectors A and B A and B with their tal brought into common origin B. The sum A plus B obtained using parallel method. C. The parallelogram method of vector addition is equivalent to triangle method. Example 4.1. Rain is falling vertically with a speed of 35 meter per second. Wind start blowing after some time with a speed of 12 meter per second in east to west direction. In which direction should a boy waiting at a bus stop hold his umbrella? Answer. The velocity of a rain and the wind are represented by the vector Vr and Vw in figure 4.7. Mm, and R in the direction of specified by the problem. Using the rule of vector addition, we see that the resultant of Vr and Vw is capital R, as so in the figure. The magnitude of R is equal to mm, under root VR square plus VW square is equal to 35 square um, plus 12 square under root um, meter per second is equal to 37 meter per second. The direction theta that R makes with the vertical is given by tan theta is equal to VW upon VR is equal to 12 upon 35 is equal to 0.343, or theta is equal to tan minus 1 and in bracket 0.343 bracket close is equal to 90 degree. Therefore the boy should hold his umbrella in the vertical plane at an angle of about 19 degree with the vertical toward the east. Resolutions of vectors. Let a small a and small b be any two non-zero vector in a plane with a different direction, and let capital A be another vector in the same plane. Figure 4.8. Capital A can be expressed as a sum of two vectors, one obtained by multiplying small a by a real number and the other obtained by multiplying small b by another real number. To see this, let O and P be the tail and head of the vector A. Then draw a straight line parallel to A, and through P a straight line parallel to B. Let them intersect at Q. Then we have A is equal to OP plus OQ plus QP. But since OQ is parallel to small a and QP is parallel to small b, we can write OQ is equal to lambda small a and QP is equal to mu small b, where lambda and mu are real numbers. Therefore, a capital A is equal to lambda small a plus mu small b. Two non-collinear vectors small a and small b, resolving a vector capital A in terms of vectors small a and small b. We say that capital A has been resolved resolved in two component vectors lambda a and mu small b, and along a small a and small b respectively. Using this method, one can resolve a vector into two component vectors along a set of two vectors. All the three lies in the same plane. It is convenient to resolve a general vector along the axis of a rectangular coordinated system using vector of unit magnitude. These are called unit vector that we discuss now. A unit vector is a vector of unit magnitude and point in a particular direction. It has no dimension and unit. It is used to specify a direction only. Unit vector along the x, y, and z axis of a rectangular coordinated system are denoted by small I, small j, and cap k cap, small k cap respectively, as so in figure 4.9a. Since these are unit vector, we have I cap is equal to j cap is equal to k cap is equal to 1. These unit vectors are perpendicular to each other. In this text, they are printed in boldface with a cap to distinguishing them from other vectors. Since we are dealing with motion in two dimension, in this chapter we required the use of only two unit vector. If we multiply a unit vector, say small n by a scalar, the result is a vector lambda is equal to lambda n. In general, a vector a can be written as a is equal to a n, where small n is a unit vector along capital A. We can now resolve a vector A in term of component vectors that lies along unit vectors I cap and j. Consider a vector A that lies in xy plane as shown in figure 4.9d. We draw lines from the head of a perpendicular to the coordinated axis as in figure 4.9b, and get vector a1 and a2 such that a1 plus a2 is equal to a. Since a1 is parallel to I I and A2 is parallel to J. We have A1 is equal to AXI and A2 is equal to AYJ, where AX and AY are real number. Thus, A is equal to AXI plus AYJ. This is represented in figure 4.9. See, the quantities AX and AY are called x and y components of the vector A. Note that Ax is itself not a vector, but Axi is a vector, and so is Yj. Using a simple trigonometric, we can express Ax and Ay in terms of the magnitude of A and the angle theta it makes with the x-axis. Ax is equal to a cos theta, ay is equal to a sin theta. As is clear from equation 4.13, a component of a vector can be positive, negative, or zero depending on the value of theta. Now we have two ways to specify a vector in a plane. It can be specified by first its magnitude a and the direction theta it makes with the x-axis, or second its component ax and ay. If a and theta are given, ax and ay can be obtained using equation 4.13. If ax and ay are given, a and theta can be obtained as follows: ax square plus ay square is equal to a square cos square theta plus a square sin square theta equal to a square is is equal to under root a x square plus a y square and tan theta is equal to a y upon a x. Theta is equal to tan 1 minus a y upon a x. Unit vectors I, j and k lies along the x, y and z axis. X, y and z axis. I, j, k. B. A vector A is resolved into its component A x and A y and along x and y axis. C. A1 and A2 expressed in terms of I and j. So for we have considered a vector lying in an xy plane. The same procedure can be used to resolve a general vector A into three components along the x, y, and z axis in three dimensions. If A, B, and y are the angle between A and the x, y, and z axis respectively, mm, we have we have ax is equal to a cos alpha, ay is equal to a cos beta, and az is equal to a y gamma. In general, we have a is equal to ax I cap plus ay j cap plus az k cap. The magnitude of vector A is equal to under root a x square plus a y square plus a z square. A position vector small r k can be expressed as r is equal to x I plus yj plus z k, where x, y, and z are the component of r and r along x, y, z axis respectively. Vectors addition analytical method. Although the graphical method of adding a vector help us the visualizing the vector and the help us visualizing of vectors and the resultant vector. It is sometimes tedious and has limited accuracy. It is much easier to add vectors by combining their respective components. Consider two vectors A and B in xy plane with components ax, ay, and bx, by. A is equal to axi plus ayj. Vector A resolves into a component along x, y, and z axis. B is equal to bxi plus byj. Later on, b there some we have r is equal to a plus b is equal to axi plus ayj bracket close plus bxi plus byj bracket close. Since vector obey the commutative and associative laws, we can arrange and regroup the vector in equation 4.9a as convenient to us. R is equal to ax plus bx into I plus ay plus by into j. since r is equal to rx I plus ryj, we have rx is equal to ax plus bx, y ry is equal to ay plus by. Thus, each component of the result vector r is the sum of the corresponding components of a and b. In three dimensions, we have a equal to ax I plus ayj plus azk. B is equal to bxi plus byj plus bzk. R is equal to a plus b is equal to rxi plus ryj plus rzk. With r reaction is equal to ax plus bx, ry is equal to ay plus by, rz is equal to az plus bz. This method can be extended to addition and subtraction of any number of vectors. For example, if vectors small a, b, and c are given as small a is equal to axi plus ayj plus azk, b small b is equal to bxi plus byj plus bzk, c is equal to cxi plus cyj plus czk. Then a vector capital T is equal to small a plus b minus c has components tac tx is equal to ax plus bx minus cx, ty is equal to ay plus b y minus c cy, tz is equal to az plus bz minus cz. Example 4.2. Find the magnitude and direction of the resultant of two vectors A and B in terms of their magnitude and angle theta between them. Answer. Let OP and OQ represent the two vectors A and B making an angle theta. Then, using the parallelogram method of vector addition, OS represent the resultant vector R is equal to A plus B. SN is normal to OP and PM is normal to OS. From the geometry of the figure, OS square is equal to ON square plus SN square, but ON is equal to OP plus PN is equal to A plus B cos theta. SN is equal to B sin theta. OS square is equal to A plus B cos theta square plus B sin theta square. R square is equal to A square plus B square plus 2AB cos theta. R is equal to under root A square plus B square plus 2AB cos theta. In a triangle OSN, SN is equal to OS sin alpha R sin A, and in triangle SN is equal to PS sin theta or B sin theta. Therefore, sin alpha is equal to B sin theta, or r upon sin theta. R upon sin theta is equal to b upon sin alpha. Similarly, pm is equal to a sin alpha is equal to b sin beta, or a upon sin beta is equal to beta b upon sin alpha. Combining equation 4.24b and 4.24c, we get r upon sin theta is equal to a upon sin beta is equal to b upon sin alpha. Using equation 4.24d, we get sin alpha is equal to b upon r sin theta, where r is given by equation 4.24a. or tan alpha is equal to yes n upon op plus pn is equal to b sin theta upon a plus b cos theta. Equation 4.24a gives the magnitude of the resultant, and equations 4.24e and 4.24 its direction. Equations 4.24a is known as law of coincidence, and equation 4.24d as the law of sines. A motorboat is racing toward north at 25 km per hour, and the water current in that region is 10 km per hour in the direction of 16 degree east of south. Find the resultant velocity of the boat. Answer the vector B representing the velocity of motorboat, and the vector V C represented the water current, are shown in figure 4.11 in direction specified by the problems. Using the parallel method of addition, the resultant R is obtained in the direction shown in the figure. We can obtain the magnitude of capital R using the law of cosine. Mm, R is equal to under root VB square plus VC square plus 2 VC cos 120 degree is equal to under root 25 square plus 10 square plus 2 into 25 into 10 10 minus 1 upon 2 is equal to 22 kilometer per hour. To alternate the direction, we apply the law of sines. mm, R upon sin theta is equal to VC upon sin phi, or sin phi mm, is equal to VC upon R sin theta is equal to 10 into sin 120 degree upon 21.8 is equal to 10 under root 3 upon 2 into 21.8 is equal to 0.39 0.397. Motion 97 is equal to 23.4 degree. Motion in plane. Motion in a plane. In this section, we shall see how to describe the motion in two dimensions using vectors. Position vector and displacement. The position vector small r of a particle p located in a plane with reference to the origin of an xy reference frame is given by r x is equal to xi plus yj, where x and y are component of r along x and y axis, or simply they are the coordinate of the object. Position vector r. D. Displacement del r, and average velocity v of a particle. As the internal del t approaches zero, the average velocity approaches the velocity v. The direction of v vector is parallel to the line tangent 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 to the path tangent to the path. Suppose a particle moves along the curve shown by a thick line, and is a at p at time t and p arc at time t arc. Figure 4.12b. the displacement is del r is equal to r arc minus r, and is directed from p to p arc. We can write equation 4.25 in a component form. Del r is equal to x arc I plus y arc j minus x I plus y j is equal to I del x plus j del y, where del x is equal to x arc minus x del y is equal to y arc minus y velocity. The average velocity vector v of an object is the ratio of displacement and the corresponding time interval. Vector v is equal to average velocity v is equal to del r upon del t is equal to del x I plus del y j upon del t is equal to I del x upon del t plus j del y upon del t, or average velocity v is equal to vector v x I cap plus vector v y j cap. Since average velocity v is equal to del r upon del t, the direction of the average velocity is the same as that of del r. In figure 4.12, the velocity instantaneous velocity is given by limiting value of the average velocity as the time interval approaches 0. V is equal to lime del r upon del t is equal to del r upon del t. The meaning of the limiting process can be easily understood with the help of figure 4.13a and 2d. In these figures, the thick line represents the path of an object which is a p at time t. P1, P2, and P3 represent the position of the object after time del T1, del T2, and del T3, and del R1, and del R2, and del R3 are the displacement of the object in times del T1, del T2, and del T3 respectively. The direction of the average velocity v vector v is shown in figure a, b, and c for three decreasing value of del t. Example, del t1, del t2, and del t3. Del t1 is greater than del t2, greater than del 3, as del t0, del r 0, and is along the tangent to the path. Therefore, the direction of velocity at any point on the path of an object is tangential to the path at that point and is in the direction of motion. We can express v in a component form. Vector v, average velocity v is equal to dr upon dt is equal to lime del t is equal to 0, del x upon del t I plus del y upon del t j is equal to I lime del t is equal to 0, del x upon del t plus j lime del t 0, and del y upon del t, or average velocity v is equal to I dx upon dt plus j dy upon dt is equal to vx I plus vyj, where vx is equal to dx upon dt, vy or dy upon dt. So if the expression for the coordinate x and y are known as function of time, we can use this equation to find vx and vy. The magnitude of v is then v is equal to under root vx square plus vy square. And the direction of v is given by the angle theta. Tan theta is equal to vy upon vx. Theta is equal to tan minus 1 vy upon vx vy, and angle theta are shown in figure 4.14 for a velocity vector v. Acceleration, the average acceleration of an object for the time interval del t moving in xy plane is the change in velocity divided by the time interval. Mm, Average velocity is equal to del v upon del t is equal to del v x I plus v y j upon del t is equal to del v x upon del t I plus del v y upon del t j. Or average acceleration is equal to ax I plus ay j. In term of x and y, ax and ay can be expressed as ax is equal to d upon dt, and dx upon dt is equal to d square x upon dt square. A y is equal to dt upon d upon dt, dy upon dt is equal to d square y upon dt square. The component Vx and Vy of velocity v and the theta angle it make with x-axis. Note that Vx is equal to v cos theta, Vy is equal to v sin theta. The acceleration, instantaneous acceleration, is the limiting value of the average acceleration as the name interval approaches zero. Mm, Acceleration is equal to lime del v upon del t. Del t is equal to 0, since del v is equal to del vxi plus del vy j, we have a equal to I lime vx upon del t plus j lime v del vy upon del t, or a is equal to axi plus ayj, where ax is equal to dyx upon dt, ay is equal to dby upon dt. As in the case of velocity, we can understand graphically the limiting process used in defining acceleration on a graph showing the path of the object motion. This is shown in figure 4.15 to D. The P presents the position of the object at time t, and the P1, P2, P3 position after time del T1, del T2, del T3 respectively. Del T1 is greater than del T2, del T3. The velocity vector at point p1 p1 p2 p3 are also shown in figure 4.15. A, B, and C. In case of del T, del T V is obtained using the triangle law of vector addition. Define the direction of average acceleration is the same as that of del V. We see that as del del t decreases the direction of del v change and consequently the direction of the acceleration change. Finally, in the limit del t 0 figure 4.15 d, the average acceleration becomes the instantaneous acceleration and has the direction as so. Figure 4.15, the average acceleration for three time intervals del t1, del t1, del t2, del t3, mm, del t1 greater than del t2 greater than del 3. In limit del t 0, the average acceleration become the acceleration. Note note that in one dimension the velocity and the acceleration of an object are always along the same straight line, either in the same direction or in the opposite direction. However, for motion in two or three-dimension velocity and acceleration vectors may have any angle between 0 degree and 180 degree between them. Example 4.4, the position of a particle is given by r equal to 3.0 t t I cap plus 2.0 t2 j plus 5.0 k cap, where t is the second and the coefficient have the proper unit for r to be in meter and find v t and a t of the particles. Find the magnitude and direction of vt at t is equal to 1.0 second. Average answer: vt is equal to d r upon dt is equal to d upon dt, 3.0 ti plus 2.0 t square j plus 5.0 k is equal to 3.0 I plus 4.0 tj. A t is equal to dv upon dt is equal to plus 4.0 j. A is equal to 4.0 meter per second square along y directions at t is equal to 1.0 second. V is equal to 3.0 I cap plus 4.0 j cap. Its magnitude is v is equal to under root 3 square plus 4 square is equal to 5.05 meter per second, and theta is equal to tan minus 1 vy upon vx is equal to tan minus 1 4 upon 3 is equal to 5 5 3 5 53 degree with the x-axis. Motion in a plane with a constant acceleration. Suppose that an object is moving in xy plane and its acceleration is constant over an interval of time. The average acceleration will equal this constant value. Now let the velocity of the object be v naught at time t is equal to 0 and v at time t. Then by definition a is equal to v minus v naught upon t minus 0 is equal to v minus v naught upon t. Or v is equal to t naught plus a t. In term of components, vx is equal to vx plus axt. Vy is equal to v v naught y plus a y t. Let us now find how the position of r change with time. We follow the method using used in the one dimension case. Let R naught and R be the position vectors of particles at time 0 and t, and let the velocity at these instant be v naught and v. Then over this time interval, the average velocity is v naught plus v upon 2. The displacement is the average velocity multiplied by the time interval. R minus R naught is equal to v plus v naught upon 2, t is equal to v naught plus at plus v naught upon 2 is 2 t is equal to v naught t plus half a t square, or r is equal to r naught plus v naught t plus 1/2 a t square. It can be easily verified that the derive of equation 4.34a, example dr upon dt, gives equal equation 4.33a, and it also satisfies the condition that at t is equal to 0, r is equal to r naught. Equations 4.34a can be written in the components form as x is equal to x naught plus v naught x t plus 1/2 a x t square, y is equal to y naught plus v naught y t plus 1/2 a y t square. On intermediate interpretation of equation 4.34b is that the motion in x and y direction can be treated independently of each other. That is, the motion in a plane two dimension can be treated as two separate simultaneous one-dimensional motion with constant acceleration along two perpendicular directions. This is an important result and is useful in analyzing motion of objects in two dimensions. A similar result holds for three dimensions. The choice of perpendicular direction is convenient in many physical situations, as we shall see in section 4.10 for projectile motion. Example Example 4.5, a particle start for origin at t equal to 0 with velocity 5.0 I cap meter per second. The move in x y plane under acceleration of a force which produce a constant acceleration of 3.0 I plus 2.0 j meter per second square. What is the y coordinate of the particle at the instant? Its x coordinate is 44 meter. D. What is the speed of a particle at this time? Answer for from equation 4.34a, for r not equal to 0, the position of the particle is given by rt is equal to v naught t plus 1/2 a t square equal to 5.0 I cap t plus 1/2 3.0 I cap plus 2.0 j cap into t square is equal to 5.0 t plus 1.5 t square into I cap plus 1.0 t square j cap. Therefore, x t is equal to 5.0 t plus 1.5 t square, y t is equal to plus 1.0 t square. given x t is equal to 84 meter and t is equal to question mark 5.0 t plus 1.5 t square is equal to 84 84 t is equal to 6 second at t is equal to 6 second y is equal to 1.06 1.0 into 6 square equal to 36 point 0 meter. Now the velocity v is equal to dr upon dt is equal to 5.0 plus 3.0 t I cap into I cap plus 2.0 tj. At t is equal to 6 second v is equal to 23.0 I plus 12.0 j. Speed is equal to v is equal to under root 23 plus 12 23 plus 12 12 square is equal to 26 meter per second. Relative velocity in two dimensions. The concept of relative velocity introduced in section 3.7 for motion along a straight line can be easily extended to include motion in a plane or in three dimensions. Suppose that two object A and B are moving with the velocity VA and VB, each with respect to some common frame of reference says ground. Then velocity of object A relative to that of B is VAB is equal to A minus B to A minus B. And similarly the velocity of object b relative to that of a is in vba is equal to vb minus va. Therefore ab is equal to minus ba. And vab is equal to vba. Example 4.6. Ran is falling vertically with a speed of 35 meter per second. A woman ride a bicycle with a speed of 12 meter per second in east to west direction. What is the direction in which she should hold her umbrella? Mm, Answer in figure 4.16 we are represent the velocity of rain and vb the velocity of bicycle. The woman is riding both these velocity are with respect to the ground. Such woman is riding a bicycle. The velocity of rain as experienced by mm, experienced by her is the velocity of rain relative to the velocity of bicycle she is riding. That is vrb equal to vr minus vb. This relative velocity vector as shown in figure 4.16 makes an angle theta with the vertical. It is given by tan theta is equal to vb upon vr is equal to 12 upon 35 is equal to 0.34 343 or theta is equal to 19 degree. Therefore, the woman should hold her umbrella at the angle of about 19 degree with the vertical toward the west. Note carefully the difference between this example and example 4.1. In example 4.1, the boys experience the resultant vector sum of the velocities will in this example of woman 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 experienced the velocity of the rail relative to the bicycle. The vector difference of the two velocities. Projectile motion as an application of the ideas developed in the previous section. We consider the motion of a projectile, an object that is in flight after being thrown or projected is called a projectile. Such a projectile might be a football, a cricket ball, a baseball, or any other object. The motion of a projectile may be thought of a result of two separate simultaneously occurring components of motion. One component is along a horizontal direction without any acceleration, and the other along the vertical direction with the constant acceleration due to the force of gravity. It was Galileo who first stated this independence of the horizontal and the vertical component of the projectile motion. In this dialogue on the Great World System, 1632, in our discussion, we shall assume that the air resistance has a negligible effect on the motion of the projectile. Suppose that the projectile is launched with the velocity v naught that make an angle theta with the x-axis, as shown in figure 4.17. After the object has been projected, the acceleration acting on it is that due to the gravity which is directed vertically downward. A is equal to minus gj, or ax is equal to 0, a y is equal to minus g. The component of initial velocity v naught are v naught x is equal to v naught cos theta angle, uh, a v naught y is equal to v naught sin theta angle. Motion of an object projectile with a velocity v naught and angle theta naught. If we take the initial position to be the origin of the reference frame as so in figure 4.17, we have x naught is equal to 0, y naught is equal to 0. Then equation 4.34 becomes x is equal to v naught x t is equal to v naught cos theta and y is equal to v naught sin theta naught t minus 1 by 2 2 g theta square. The component of a velocity at time t can be obtained using question 4.33b. V max is equal to v naught x is equal to v naught cos theta naught, y is equal to v naught sin theta naught minus the gt. Equation 4.38 gives the x and y coordinate of the position of a projectile at time t in term of two parameters: initial speed v naught and projectile angle theta naught. Notice that the choice of mutually perpendicular x and y direction for the analysis of the projectile motion has resulted in a simplification on the component of the velocity. X component remain constant throughout the motion, and only the y component change, like an object in free fall in vertical direction. This is shown graphically at pure instant in figure 4.40. Note that at the point of the maximum height, Vy Vy is equal to 0, and therefore theta is equal to tan minus 1. Vy upon Vx is equal to 0. Equation of path a projectile What is the space of the path followed by the projectile? This can be seen by eliminating the time between the expressions for x and y as given in equation 4.38. We obtain y is equal to tan theta x minus g upon 2 v naught cos theta naught square x square. Now since g theta naught and v naught are constant, equation 4.14 is of the form y is equal to ax plus bx square, in which a and b are constant. This is the equation of a parabola. Example: the path of the projectile is a parabola. Mm, mm, Figure 4.18. The path of a projectile is a parabola. Time of maximum height. How much time does a projectile take to reach the maximum height? Let this time be denoted by a small tm, since at this time point vy is equal to 0. We have from equation 4.39 vy is equal to v naught sin theta naught minus gtm is equal to 0. Tm is equal to v naught sin theta naught upon g. The total time tf during which the projectile is in flight can be obtained by putting y is equal to 0 in equation 4.38. We get tf is equal to v naught sin theta upon g. Tf is known as the time of flight of the projectile. We note that Tf is equal to 2Tm, which is expected because of the symmetry of the parabolic path. Maximum height of a projectile. The maximum height hm reached by the projectile can be calculated by substituting t is equal to tm in equation 4.38. Y is equal to hm is equal to v naught sin theta naught v naught sin theta naught upon g minus g to g upon to v naught sin theta upon g square. Or Sm is equal to v naught sin theta naught square upon 2g. Horizontal range of a projectile. The horizontal distance traveled by a projectile from its initial position x is equal to y is equal to 0 to the position where it passes y is equal to 0 during its fall is called the horizontal range. R it is the distance traveled during the time of flight tf. Therefore the range r is equal to v naught cos theta naught t into tf. V naught cos theta naught into 2 v naught sin theta naught upon g. Or r is equal to v naught square sin 2 theta naught upon g. Equation 4.43a. So that for a given projectile velocity v naught r is a maximum when sin 2 theta is a maximum when theta is equal to 45 degree. The maximum horizontal range is therefore rem is equal to v naught v naught 2 upon g. Example 4.7. Galileo in his book Two New Science stated that for elevation which excite or fall short of 45 degree by equal amount of range are equal. Prove this statement. For a projectile launched with velocity v naught at angle theta naught. The range is given by r is equal to v naught square sine 2 theta naught upon g. Now for the angle 45 degree plus plus alpha and 45 degree minus alpha 2 degree 2 theta naught is 90 degree plus 2 alpha and 90 degree minus 2 alpha respectively. The value of sine 90 plus 2 alpha and sine 90 minus 2 alpha are the same equal to that of cos 2 alpha. Therefore, range are equal for elevation which exceed or fall short of 45 degree by equal amount alpha. Example 4.8. A hiker stand on the edge of a cliff 490 meter above the ground and throw a stone horizontally with an initial speed of 15 meter per second, and neglecting air resistance. Find the time taken by the stone to reach the ground and the speed with which it hits the ground. Take z is equal to 9.8 meter per second square. Mm. Answer. We choose the origin of the x and y axis at the edge of the cliff and t is equal to 0 second at the instant the stone is thrown. Choosing the positive direction of x axis to be along the initial velocity and the positive direction of y-axis to with the vertically upward direction. The x and y component of the motion can be treated independently. The equation of the motion are xt is equal to x naught plus v naught x t. Yt is equal to y naught plus v naught y t plus 1/2 to a y t2 square. Here x naught is equal to y naught is equal to 0, v naught y is equal to 0, a y is equal to minus g is equal to minus 9.8 meter per second square. V naught x is equal to 15 meter per second. The stone hit the ground when vt is equal to minus 419 meter. Minus 419 meter is equal to minus 1 by 2 9.8 t2. This value t is equal to 10 second. The velocity component are v x is equal to v naught x and y x is equal to y naught x minus gt. So that when the stone hit the ground, v naught x is equal to 15 meter per second and v naught y is equal to minus 0 minus 9.8 into 10 is equal to minus 98 meter per second. Therefore, the speed of the stone is under root v x square plus vy square is equal to 50 square under root 15 square plus 98 square is equal to 99 meter per second. Example. Example 4.9. A cricket ball is thrown at a speed of 28 meter per second in a direction 30 degree above the horizontal. Calculate A. The maximum height. B. The time taken by the ball to return to the same level. And C. The distance from the thrower to the point where the ball return to the same level. Answer A. The maximum height is given by H.M. is equal to V naught sin theta naught square upon 2G is equal to 28 sin 30 square upon 9.2 into 9.8 meter. 14 into 14 upon 2.98 is equal to 10.0 meter. The time taken to return to the same level is Tf is equal to 2 V naught sin theta naught upon G equal to 2 into 28 into sine 30 degree upon 9.8 is equal to 28 upon 9.8 second is equal to 2.9 second. C. The distance from the thrower to the point where the ball returned to the same level is r equal to v naught square sine 2 theta upon g is equal to 28.20 28 sorry 28 into 28 into sine 16 degree upon 9.8 is equal to 96 meter. No, 69 meter. 69 meter. Neglecting AR resistance, what does the Egyptians really means? While treating the topic of projectile motion, we have stated that we assume that the air resistance has no effect on the motion of the projectile. You must understand what the statement really mean. Friction force due to the viscosity, air resistance are all dispositive force in the presence of any of such force opposing motion. Any object will lose some part of its initial energy and consequently moment to thus a projectile that transverse a parabolic path would certainly show deviation from its idealized trajectory. In the presence of air resistance, it will not hit the ground with the same speed with which it was projected from it. In the absence of air resistance, the x component of the velocity remain constant and it is only the y component that undergoes a continuous changes. However, in the presence of air resistance, both of these would get affected. That would mean the range would be less than the one given by equation 4.43. Maximum height attained would also be less than that predicted by equation 4.42. Can you then anticipate the change in the time of a flight? In order to avoid air resistance, we will have to perform the experiment in vacuum or under the low pressure, which is not easy when we use the phrase like neglected air resistance. We imply the change in parameters such as range, height, etc. is much smaller than their value without air resistance. The calculation without air resistance is much simpler than that with air resistance. Uniform circular motion. When an object follow a circular path at a constant speed, the motion of the object is called uniform circular motion. The word uniform referred to the speed which is uniform constant throughout the motion. Suppose an object is moving with the uniform speed v in a circle of radius as shown in figure 4.19. Since the velocity of the object is changing continuously in a direction, the object undergoes acceleration. Let us find the magnitude and the direction of this acceleration. Velocity and acceleration of an object in uniform circular motion. The time interval del t decreases from to where it is zero. The acceleration is directed at each point of the path toward the center of the circle. Let R and R be the position vectors, and V arc the velocity of the object when it is at point P, and P arc as shown in figure 4.90a. By definition, velocity at a point is along the tangent at that point in the direction of motion. The velocity vector V and V arc are as shown in figure 4.90 A1. V Del B is obtained in figure 4.90 using the triangle law of vector addition. Since the path is circular, V is perpendicular to R and so is V arc to R arc. Therefore, del V is perpendicular to del R. Since average acceleration is along del V, in average velocity A is equal to del V upon del T. The average acceleration A vector is perpendicular to del R. If we place del V on the line that bisects the angle between R and R arc, we see that it is directed toward the center of the circle. Figure 4.90b show the same quantities for smaller time interval. Del V and hence vector A is again directed toward the center in figure 4.90c. T del T0 and the average acceleration becomes the instantaneous acceleration. It is directed toward the center, and thus we find that the acceleration of an object in a uniform circular motion is always directed toward the center of the circle. Let us now find the magnitude of the acceleration. Mm, the magnitude of A is by the definition given by A is equal to lime del T zero V del V upon del T. Let the angle between the position vectors R and after R and R can be del theta. Since the velocity vectors V and V arc are always perpendicular to the position vector, the angle between them is also del theta. Therefore, the triangle CP arc performed by the position vector and the triangle GHI performed by the velocity vector V arc and del V are similar. Figure 4.90a. Therefore, the ratio of the base length to side length for one of the triangle is equal to that of the other triangle. That is del V upon V is equal to del R upon R. Del V is equal to V del R upon R. Therefore, A is equal to lime del T 0. Del V upon del T is equal to lime del T 0. V del R upon capital R A T R del T is equal to V upon capital R lime del T is equal to 0 and del R upon del T. If del T is small, del theta will also be small, and then arc P arc can be approximately taken to be del R is equal to V not V del T del R upon del T is equal to V or lime T 0 A del R upon del T is equal to V. Therefore, the centripetal acceleration AC is equal to V upon R. V is equal to V square upon capital R. Thus, the acceleration of an object moving the speed V in a circle of radius capital R, the R has a magnitude V square upon R and is always directed toward the center. This is why the acceleration is called centripetal acceleration, a term proposed by Newton through analysis of centripetal acceleration was first published in 1673 by the Dutch scientist Christian Huygens 1629 to 1695, but it was probably known to Newton also some year earlier. Mm, Centripetal comes from Greek term which means center seeking. Since V and R are constant, the magnitude of the centripetal acceleration is also constant. However, the direction change pointing always toward the centimeter. Therefore, a pointing always toward the centimeter. Therefore, a centripetal acceleration is not a constant vector. We have another way of describing the velocity and the acceleration of an object in uniform circular motion as the object moves from P to P arc in time del T is equal to T arc minus T. The line CP figure 4.19 turn through an angle theta an angle theta as so in figure del theta is called angular distance. We define the angular speed omega, Greek letter omega, as the time rate of change of angular displacement. Omega is equal to del theta upon del t. Now, if the distance traveled by the object during the time del t is del s, mm, P arc is del s, then V is equal to del s upon del t, but del s is equal to r del theta. Therefore, V is equal to r del theta upon del t is equal to r omega, where V is equal to r omega. We can express the centripetal acceleration AC in a term of angular speed. AC is equal to V square upon R is equal to omega square R square upon R is equal to omega square R. AC is equal to omega square R. The time taken by an object to make one revolution is now as its time period T, and the number of revolutions made in 1 second is called its frequency. V is equal to 1 by T. However, variable. During this time, the distance moved by the object is s equal to 2 pi r. Therefore, v equal to 2 pi r upon t is equal to 2 pi r v. In a term of frequency we have omega is equal to 2 pi v is equal to 2 pi r v. AC is equal to 4 pi square v square r. Example 4.10. An insect trapped in a circular groove of radius 12 centimeter moves along the groove steadily and complete 7 revolutions in 100 seconds. What is the angular speed and the linear speed of the motion? Is the acceleration vector as a constant vector? What is the magnitude? Answer. This is an example of uniform circular motion. Here r is equal to 12 centimeter. The angular speed omega is given by omega is equal to 2 pi upon t is equal to 2 pi into 7 upon 100 is equal to 0.14 radius per second. The linear speed v is equal to omega r is equal to 0.44 second into 12 centimeter is equal to 5.3 centimeter per second. The direction of velocity v is along the tangent to the circle at every point. The acceleration is directed toward the center of the circle. Since this direction changes continuously, acceleration here is not a constant vector. However, the magnitude of acceleration is constant. A is equal to omega square r is equal to 0.44 per second. 12 centimeter is equal to 2.3 centimeter per second square. Summary. Scalar quantity are quantities with magnitude only. Example are distance, speed, mass, and temperature. Vector quantity are quantity with magnitude and direction both. Example are displacement, velocity, and acceleration. They obey special rule of vector algebra. A vector a multiplied by a real number lambda is also a vector whose magnitude is lambda time the magnitude of the vector a and whose the direction is the same or opposite depending upon whether lambda is positive or negative. Two vectors A and B may be added graphically using a head-to-tail method or parallelogram method. Vector addition is commutative. A plus B is equal to B plus A. It is obey the associative law. A plus B plus C is equal to A B plus C. A null or zero vector is a vector with zero magnitude. Since the magnitude is zero, we don't have into spatial its direction. It has the properties a plus zero is equal to a lambda o is equal to zero. Zero a is equal to zero. The subtraction of a vector b from A is defined as the sum of A and minus b. A vector can be resolved. Yeah, a minus b is equal to a plus minus b. A vector A can be resolved into component along to given vector small a and small b lying in the same plane. A is equal to lambda A plus mu b, where lambda and mu are real number. The unit vector associated with a vector A has magnitude 1 and is along the vector A. n is equal to capital A upon in bracket capital A, the unit vector I j k are vector of unit magnitude and point in the direction of the x y and z axis respectively. In a right-handed coordinate system, a vector can be expressed as a is equal to ax I plus a yj, where ax a y are its component along x and y axis. If vector a make an angle theta with the x axis, then ax is equal to a cos theta, a y is equal to a sin theta, and a is equal to a under root ax square plus a y square tan theta is equal to a y upon ax. Vector can be conveniently added the using analytical method if sum of two vector a and b that lies in x y plane is r, then r is equal to rx I plus ryj, where rx is equal to ax plus bx and ry is equal to ay plus by. The position vector in the position vector of an object is x y plane is given by r is equal to x I plus y j, and the displacement from the position x to the position r arc is given by del r is equal to r arc minus r is equal to x arc minus x I plus y arc minus y j is equal to del x I plus del y j. If an object undergoes a displacement del r in time del t, its average velocity is given by v is equal to del r upon del t. The velocity of an object at time t is the limiting value of the average velocity. As del t tend to zero, v del t is equal to zero, lime del r upon del t is equal to del r upon del t. It can be written in unit vector notation as v is equal to vxi plus vyj plus vjk, where vx is equal to dx upon dt, and vy is equal to dy upon dt, and vj is equal to dz upon dt. Where when position of angle of when position of an object is plotted on a coordinated system, v is always tangent to curve um, representing to path of the object. If the velocity of an object changes from v to v arc in time del t, then its average acceleration is given by a equal to vector a is equal to v minus v arc upon del t is equal to del v upon del t. The acceleration at any time t is the limiting value of a vector a as t0 a is equal to lime t0 del v upon del t is equal to dv upon dt. Each component from v have a is equal to axi plus a yj and a zk, where ax is equal to dx dvx upon dt, ay is equal to dvy upon dt, az is equal to dvz upon dt. If an object is moving in a plane with constant acceleration, a is equal to a under root a is equal to a under root a x square plus a b a y square, and its position vector at time t is equal to 0 is r naught, then at any other time t it will be at a point given by r is equal to r naught plus v naught t plus 1 by 2 at square, and its velocity is given by v is equal to v naught plus at, where v naught is the velocity at time t is equal to 0. It components from x is equal to x naught plus v naught x t plus 1 half a x t square, y is equal to y naught plus v naught y t plus 1 half a y t square, x is equal to v naught v x is equal to v naught x plus a x t, v y is equal to v naught y plus a y t. Motion in a plane can be treated as a superposition of two separate simultaneous one dimensional motion along two perpendicular direction. An object that is used in flight after being projected is called a projectile. If an object is projected with the initial velocity v naught, making an angle theta with x-axis, and if we assume its initial position to coincide with the origin of the coordinate system, then the position and velocity of the projectile at time t are given by x is equal to v naught cos theta t, y is equal to v naught sin theta, sin theta not t minus 1 half gt square, vx is equal to a vx is equal to v naught ax is equal to v naught cos theta naught, mm, vy is equal to v naught sin theta naught minus gt. The path of a projectile in parabolic and is given by y is equal to tan theta naught x minus g x upon 2 v naught cos theta is square. The maximum height that a projectile attains is. Yes, m is equal to v naught sin theta naught square upon 2g. The time taken to reaches this height is tm is equal to v naught sin theta upon g. The horizontal distance traveled by a projectile from its initial position to the position it passes y is equal to 0 during its fall is called the range r of the projectile. It is r is equal to v naught square upon g sin 2 theta naught. When an object follows a circular path at constant speed, the motion of the object is called uniform circular motion. The magnitude of its acceleration is ac is equal to v square upon r. The direction of AC is always toward the center of the circle. Mm, the angular speed omega is the rate of change of angular distance. It is related to velocity v by v is equal to omega r. The acceleration is ac is equal to v omega square r. Mm. If t is the time period of revolution of object is circular motion, and v is its frequency, we have omega is equal to 2 pi v, and v is equal to 2 pi v r. AC is equal to 4 pi square v square r. physical quantity symbol dimension unit remark position vector small r dimension l unit meter m and vector it may be denoted by any other symbol well do as well displacement del r equal small m due velocity average velocity vector v and initial velocity v dimension l2 lt minus 1 lt minus 1 meter per second mm, average del r upon del t vector and dr upon dt vector acceleration average am and initial dimension lt minus 2 meter per second square average is equal to del v upon del t vector and instantaneous is equal to dv upon dt vector. Projectile motion time of maximum height t m Tm is equal to T dimension and unit second time of maximum height V naught sin theta upon G maximum height SM L dimension unit meter equal to V naught sin theta naught square upon 2G horizontal range r dimension liter unit meter v naught square sin 2 theta upon g circular motion angular speed omega centripetal acceleration ac omega dimension t minus 1 centripetal acceleration lt minus 2 angular speed radian per second unit meter per second square unit del theta upon del t is equal to v upon r and v स्क्वायर अपॉन आर सेंटीपीटल एक्सीलरेशन। यहाँ पर हम लोग का खत्म हो रहा है। ठीक है, इधर एक्सरसाइज बचा है और इसके बाद है लॉ ऑफ मोशन चैप्टर 5। ठीक है, इसको हम बाद में करेंगे।